Okay, this is part 2, section 4.1. We're looking at scatter diagrams and correlations. So we've got a data set here, the weight of a car versus miles per gallon. So we got an engineer wanted to determine how the weight of a car affects miles per gallon. So the following data represents weights of various domestic cars and their gas mileage in the city for 2015 model year vehicles. So first we want to determine, so we got weight, miles per gallon, which variable is likely the explanatory variable and which is likely the response variable. And if you think about this here, for the, I'll put EXP, for the explanatory variable, this is going to explain the response variable. And so the explanatory variable here would definitely be the weight, because that weight of the car is going to have significant bearing on the miles per gallon. So our explanatory variable, again, is going to be the weight, because it's going to explain or give reason as to why the miles per gallon is what it is. As we increase that weight, we probably assume that miles per gallon is going to decrease and vice versa. Okay, secondly, we're going to draw a scatter diagram of our data. So I've got our data in StatCrunch here. So we're going to go under graph here. We're going to do a scatter plot is what StatCrunch calls it. So the x variable, which is going to be on the horizontal, so that's our explanatory, would be weight, and our y variable, which is on the vertical, would be our miles per gallon. Okay, and we don't need to change up any of these other things, so we're just going to compute. And we can see here is a look at our data in a scatter diagram. And notice that we are not at 0, 0, but you can just see, and if I hover over these, it would talk about every point, but you can just see this general trend downwards, although this guy is going to kind of throw us off a little bit. Okay, so that would be drawing the scatter diagram. Again, you can use StatCrunch. I don't expect you to try and get out your art tools and create one. Okay, next we want to compute the linear correlation coefficient between the weight of the car and its miles per gallon in the city. So if we come back to StatCrunch, I'm going to go under Stat and Summary Stats, and I'm going to find correlation. And I want weight and miles per gallon, so I hold down the Shift key, grab both of those, and I'll compute and see that I get a correlation coefficient of negative 0.8415, so I'll just go negative 0.842. So the correlation coefficient is negative 0.842. So that's a pretty strong negative correlation, as would be expected. And so then our next question is, does a linear relation exist between the weight of a car and its miles per gallon in the city? So how are we going to determine this? So here's how we're going to determine it. If we're testing for a linear relation, what we do is we determine the absolute value of our correlation coefficient. So in our case, the absolute value of that correlation coefficient would be the absolute value of negative 0.842, which is 0.842. Absolute value just means a distance from 0. Okay, then once we have that, we find a critical value in table 2 in this textbook, but this will pop up in your class for you. Okay, and so here are the critical values right here, and they're based off of the sample size. And then if the absolute value of the correlation coefficient is greater than the critical value, we say that a linear relationship or relation exists between the variables. Otherwise, if it's not, then it doesn't. So just another way to think about the procedure is to consider this figure below. So if the correlation coefficient is positive and greater than the critical value, the variable is positively associated. If the correlation coefficient is negative and less than the opposite of the critical value, the variable is negatively associated. So if we've got our critical value, say right here, anything that falls below or above is going to be more extreme, so it's going to be either more negative or more positive, and that will tell us that there is a linear relationship. It exists between these two variables. So coming back up real fast, we've got, in our case, we got a sample size of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So our sample size is 10. So 10 is got a critical value of 0.632. So the absolute value of our correlation coefficient, remember that was 0.842. That is greater than 0.632. And so we would say that a linear relation exists. Okay, so again, the critical value is dependent upon the sample size, and we look at the absolute value, or the distance from zero, of our correlation coefficient and compare the two. If the absolute value of the correlation coefficient is greater, then we say a linear relation exists. Okay, now we're going to look at, and this is going to help us look at the idea of resistance of the correlation coefficient. So let's suppose that we added a Ford Taurus to the data in our problem, and the Ford Taurus weighs 3,917 pounds and gets 19 miles per gallon. Okay, so we'd want to redraw the scatter diagram. So I'm going to add an 11th car here. So it was 3,917, and it got 19 miles to the gallon. Okay, so we're going to redraw the scatter diagram. So again, that was on the graph scatter plot, and our response variable, our explanatory variable, which was x, was the weight. Response variable, which is our vertical, or y, is miles per gallon. Okay, and so we added in the torus. It's going to be somewhere up in here. Okay, right there. So we get that extra point in there, and now we want to recompute the linear correlation coefficient with that torus included. So now I'm going to go under stat, summary stats, correlation. I'm going to grab these two and compute, and notice that our correlation coefficient bumps, it goes down a little bit, but it gets a little bit stronger. So R is negative 0.844. So we want to compare these results with what we saw in number 29. And if we just think about it, in number 29 we saw, so from number 29, R was negative 0.842. And you know, why are the results we got in our correlation coefficient and our scatter diagram reasonable? It's because remember the point here for the Ford Taurus was very much in line with our other points, and so we wouldn't expect much to change as far as our scatter diagram and our correlation coefficient. It got a little bit stronger because we've added another piece of evidence that goes kind of in line. But you know, in general, it follows the overall pattern that we saw. Now let's suppose that that we add a Ford Fusion hybrid to the data in problem number 29. So we're going to remove the torus that we had. So we're going to remove this guy, and we're going to add a Fusion hybrid which weighs 3,639 pounds and gets 44 miles to the gallon in the city. So it weighs 3,639 and it gets 44 miles to the gallon. Okay, now notice this is quite a bit different than the overall pattern that we had. So when I create a scatter plot. Okay, notice what happens. We have this one point, this hybrid, that throws everything off quite a bit. So you notice that this thing is really out of the norm compared to the other points that we have. So it really changes our scatter diagram. Our miles per gallon, we had to get a lot bigger on this vertical axis. Okay. So now we want to recompute the linear coefficient with the Ford Fusion. So again, under Stat, Summary Stats, Correlation, grab these two, and notice that our correlation coefficient drops way, way down to negative 0.331. So down here, R equals negative 0.331, and so that shows that the correlation coefficient is not resistant. We have one vehicle that we added that was well out of the ordinary, and it completely changed our correlation coefficient substantially. So why does this observation not follow the pattern of the data? Okay, well, the Ford Fusion noted is a hybrid, which runs on electricity and gas, whereas it's probably fair to assume that the others are not hybrid vehicles. So it's a different type of vehicle. So it's likely not the same type of vehicle. Okay, so I've gone through, I've shown you in StatCrunch, but if you need to pause the video and just take some notes as to how you get these things, there it is right there, but I've shown you how to do that. Our last question deals with correlation and causation. So we've got crime rate and we got cell phones. So the linear correlation coefficient between violent crimes and percentage of population that has a cell phone is negative 0.918 for years since 1995. Okay, so do you believe that increasing the percentage of the population that has a cell phone will decrease violent crime rate? So again, that negative correlation means that as crime goes up, cell phones go down, or vice versa. As cell phones go up, those number of people owning cell phones go up, the crime rate goes down. Do you believe that increasing that percentage will decrease violent crime? If you do, then you would just slap everyone, give every possible person a cell phone, and then crime rate should fall. But in this case, I would say no. I don't believe that increasing the population's or the amount of people in the population that have a cell phone will decrease violent crime. So we look at this idea of what's a lurking variable between percentage of population with cell phone and violent crimes rates. And one lurking variable, so a lurking variable, and this just means something that could be happening in the background. So one lurking variable could be the economy and the availability of cell phones. Because if the economy is good, then there is a lot of data that shows a strong economy tends to decrease violent crimes. And if you have a strong economy, then consumers are more likely able to buy a cell phone. So here we've got two things that are very, very correlated. We've got data, we've got a substantially strong correlation, but that does not mean that one causes the other. I hope you can see that if you just give everyone a cell phone, that does not cause violent crime to decrease. You can have these other variables just kind of lurking in the background that would be much better explaining the linear correlation that exists there. So again, correlation, causation, not the same thing. So cell phone